Assalamualaikum and salam sejahtera. This is KL2151 Makmal Elektrik dan Elektronik 2. My name is Dr. Iskandar Yahya and this is lab briefing for Lab 2 Diode Circuits. Let's look at the lab outcome. By the end of this lab session, you should be able to construct and test diode circuits and understand the applications of diodes in circuits. The prerequisite for this lab session are knowledge on ideal diode characteristics and equations, circuit construction on breadboard or protoboard, and the operation of DC supply, multimeter, function generator, and oscilloscope. The equipment and components needed are a DC supply from your IDL, an oscilloscope with 2 oscilloscope probes, a function generator, a breadboard or a protoboard, several types of diodes, which are silicon, germanium, and xenon diodes, capacitors, and resistors. The lab instruction has been uploaded in iFolio, and for part B, the question is based on your lab day. The pre-lab work has also been uploaded on iFolio. Make sure you have done your pre-lab accordingly. You must bring along a proof of your own pre-lab. Please do your circuit simulation for your pre-lab as well. You need to do simulation for all the circuits that you will be constructing in your lab session. You can use the following circuit simulation software and websites. Before we move on, let's look at some of the diode characteristics theory. What is a PN diode? A PN diode is a two-terminal semiconductor device. It is made out of two types of materials, which are a P-type semiconducting material and an N-type semiconducting material. When these two types of semiconducting materials are brought together, they will form a junction in between them. This junction is what we call the depletion junction or a depletion region, and it is responsible in making the device rectifying. It is rectifying because it allows current to flow only in one direction and not in the other direction. On your device, a normal PN diode will have a line indicating where the cathode is. A diode can be connected in two ways. One is in forward bias and secondly in reverse bias. In forward bias configuration, the anode of the PN diode is connected to the positive side of the battery or your power supply. In a reverse bias configuration, the anode of your diode is connected to the negative of your supply. Now let's look at the IV characteristics of a PN diode. A normal PN diode will have an IV characteristics ideally that looks like the red line. But in reality, the IV characteristics looks more like the blue line. On the blue line, there are some important features that you need to know. First of all, the turn-on voltage, VD, the reverse saturation current, and also VBR, which is the breakdown voltage. I will now show you some example circuit simulations for all the circuits that you have to construct in part A, which are the half-wave rectifier, a full-wave rectifier, and a voltage regulator. I'll be using Circuit Lab in this example. For the first one, which is half-wave rectifier, the half-wave rectifier should function as a rectifying circuit to rectify an AC signal into a DC signal. So your output should look something like this. Construct the circuit as in the picture shown. You must connect your oscilloscope probes to monitor the output and also the input voltages. From your oscilloscope, you should be able to see both the input and output. So here, the input is in yellow color and the output is in blue color. See how the half-wave rectifier have rectified the positive half cycle of the AC signal and then rectify any negative bias. Pay close attention to also the amplitude of both signals. They might be different, but you need to understand why they are. Now let's do the circuit simulation. Open the Circuit Lab workbench and construct the half-wave rectifier circuit. Make sure that all the components are connected properly. Also, make sure that the components have the right values or specification. For your resistor, it should be 10 kilo ohms. The diode, it should be a PN diode 1N4002. For your AC signal, make sure it has what amplitude of 1 volt or 2 volts peak to peak, and the frequency is 1 kHz. After you are satisfied with your circuit, click Simulate, and then we will run a time domain analysis. For the start time, let's put there 1 second, and the stop time, let's put there 1.005 seconds. The reason why we start with 1 second is to give time for the circuit to stabilize itself before looking at the output signals. Otherwise, if you have a capacitor, sometimes at the very beginning of the simulation, the circuit is not stabilized yet and the output signals are not really correct. For the time step, let's have as many time step as we can. So let's put there 0.0001 seconds. And we are looking at the input voltage and also the output voltage. And then we'll click Run Time Domain Simulation. Now the simulation has been completed, and this is what your waveform should look like. So the blue one, or the cayenne color, is your input voltage, and the yellow one is your output voltage. So this is exactly what you are looking for, because the circuit now is operating as a half-wave rectifier. Only the positive half cycle of the AC input signal is rectified. Again, as you can see, there is a difference in amplitude for the input and output voltage. You need to understand why this is the case. Now let's look at the second circuit, which is our full wave rectifier. Like the half wave rectifier, a full wave rectifier rectifies an AC signals, but instead of cutting off the negative half of the AC signals, it converts the negative half into a positive half. So therefore, effectively converting an AC signal into a DC signal. This is how your circuit should be constructed and look like. For this purpose, you cannot simply put the probe to be at the output and another probe to the input. Because if you do this, you won't be able to see clearly what is the output voltage. Alright, you will get something like this, which is not correct. So what you need to do is to connect one probe into one side of the resistor and another probe onto the other side of the resistor. When you do this, effectively what you're doing is trying to do an operation whereby we want to know the voltage across the resistor. So we measure the voltage at one point of the resistor and then minus that voltage to the voltage at the other end of the resistor. So effectively, we know exactly what is the voltage across the resistor. So that is what we want to measure. So to do that, one probe goes to one side of the resistor and the other one goes to the other. Alright, so and then on your oscilloscope, you can click math, do an operation, and then do an operation of one channel minus the other channel. And you should get the potential difference across the resistor. Now let's do the simulation for our full wave rectifying circuit. Construct the circuit as such, and of course make sure that all the component values are correct, especially your resistor. It should be 10 kilo ohms. Okay, and then you should add a ground on your circuit like this. This is important because otherwise your simulation program does not know where the reference voltage is and therefore cannot measure what is your Vout. Now once you are happy with your circuit, click simulate, and we are doing also time domain analysis. Start time at 1 second, stop time at let's say 0.01 second, and time step is 0.00001. Now the more time step you have, the smaller your time step is, the more accurate your curve will be, but it will take longer time for the simulation to run. And we are looking at the input voltage, and also we are looking at the output voltage. We can remove the currents because we are not interested in the currents. And once you're happy with all the settings, you can click Run Time Domain Simulation. As you can see, it's a bit slow and it will take some time to complete. Okay, so once the simulation has complete, you can look at both the input and output waveforms. So as you can see, now the negative half cycle of the AC signal has been rectified and converted into positive. So everything now is in DC. Alright, but again, as you can see, the amplitude of the output is much smaller than the input, and you need to understand and investigate why this is the case. Now for the third circuit is our voltage regulator circuit. As the name suggests, this circuit will regulate the input to make sure it will not exceed a certain limit or threshold voltage that you set. For this example, if we set the threshold voltage of this circuit to be 5 volts, regardless of whatever the voltage at the input is, the output will not exceed 5 volts. So 5 volts is the maximum voltage output that it will produce. In a voltage regulator circuit, we use a Zener diode. So we want to investigate what is the breakdown voltage of this Zener diode. And for that, we must do this experiment. And before that, of course, we need to simulate the circuit first. Now let's do the simulation for our voltage regulator circuit. The circuit itself is fairly simple. You have two identical resistors. One is R, which is our protection resistor, and then RL is our load resistor. Both has a value of 1 kilo ohms. And then you have your DC supply. Make sure it is a DC supply. And then you have a Zener diode. Make sure that the orientation is correct or the polarity is correct. And you must also have a ground. So to simulate, click simulate, and then we are doing what we call a DC sweep. A DC sweep means we are trying to sweep the input voltage from 0 all the way to 15 volts. So click parameter and choose what parameter we are using. We are using V1, this one, V1. Click V1. Sweep type linear, start from 0 volts all the way to 15 volts. And then the step size is, let's say, 0.5 volts. To add expression, we need to know what we are trying to plot. So we would like to look at the voltages, the input voltage and also the output voltage, and also what is the voltage across the Zener diode and also the load resistor as well. So add expression, click the V1, and then click add the diode, and click add the resistor. So when you do that, you have the voltage across the diode, the current that goes through the diode, voltage across the load resistor, and the current through the load resistor. And when you are happy with all the settings, click Run DC Sweep, and this is what we get. Let's look at the first graph. The first graph is showing voltage versus voltage. Basically, what we are looking at is what are the voltage across the resistor, load resistor, and also across your diode. So the blue line or the green line here is basically your input voltage. So it goes from 0 all the way to 15. But as the input reaches 10 volts, the voltage across the load resistor will saturate at 4.9 volts all the way. Even if the input voltage goes up beyond 10 volts, up until 15 volts, all right, the volt is regulated at the output within 5 volts only. So this is what we mean by a voltage regulator, because at the output, it will limit the voltage to be at 5 volts only, regardless what the input is. Below here, you have your current versus input voltage. So as you can see, this blue line or the green line is the current through your diode. So when the voltage input is less than 5 volts, no current is flowing through the diode, because the diode is connected in reverse bias configuration with respect to the supply. Therefore, no current is flowing until when the reverse bias is large enough that it exceeded its breakdown voltage when it starts to conduct. So when the Zener diode starts to conduct, all right, it will limit the voltage at the output. For your lab report, you need to produce individual report, handwritten, and submit on the following day. Check rubric for marking scheme on iFolio, and you must include your pre-lab work in your report. That's all from me today, and have fun with your lab session.